The QSK-19 fuel system is the newest in fuel technology from Cummins. The QSK-19 fuel system offers infinitely variable injection timing using a simple, efficient design with injection pressures beyond any current Cummins fuel system. Currently, the QSK-19 fuel system is being used on the new Quantum System K19 or QSK-19 engine, which is intended for heavy-duty industrial applications. In the future, Cummins will bring the efficiency of the QSK-19 fuel system to other engine platforms as well. The QSK-19 fuel system features a mechanically actuated open nozzle type injector. And, using the latest generation of Cummins electronic controls, provides precise fuel management and infinitely variable injection timing. The QSK-19 fuel system can be divided into hydromechanical components and electronic control system components. Let's start by looking at the hydromechanical components. This schematic provides an overview of the hydromechanical system of the QSK-19 fuel system. Fuel filter head and fuel filter element, fuel pump, fuel control valve assembly, fuel manifolds, QSK-19 injector, and fuel cooler. Fuel flow from the supply tank is directed to the dual fuel filter head. The fuel filters have water separators and elements that filter down to 10 microns. Water separator elements are mandatory as the actuators in the control valve body are sensitive to water. The maximum inlet restriction at the filters is 4 inches of mercury with a clean filter and 8 inches of mercury with a dirty filter. From the filters, fuel flow is directed to the inlet of the gear pump. The fuel pump is a version of the current PT fuel pump family. The gear pump generates the system flow and pressure. The fuel inlet is on the side of the gear pump housing. From the gear pump outlet, the fuel flows through the filter screen and then to either the pump outlet or the governor assembly. The filter screen is utilized to prevent any pump debris from reaching the fuel actuators. The governor assembly regulates the gear pump output, providing variable flow and pressure to match engine RPM. The governor assembly vents or spills all excess fuel back through a check valve to the gear pump inlet. The check valve maintains fuel pump housing pressure. The regulated flow output from the gear pump is directed to the PT pump outlet. A check valve in the outlet port controls backflow when the engine is not running. The PT pump does not contain throttling or AFC capabilities. The PT pump was selected because it provides excellent pressure characteristics over the complete RPM range. The core of the QSK-19 fuel system is the control valve assembly. Fuel flow produced by the pump is delivered to the control valve assembly. The assembly consists of a shutdown solenoid valve, 2 fuel actuator valves, and 2 fuel pressure sensors. The ECM mounts on the front of the assembly housing. The control valve assembly has 1 fuel inlet port and 2 outlet ports. Each outlet port is controlled by a separate actuator. The fuel rail actuator controls the fuel required for combustion. The timing fuel actuators control the fuel necessary to control injector timing. The QSK-19 fuel system utilizes the pressure time concept like the PT fuel system. The PT is completely mechanical and relies on mechanically adjusted flow areas to regulate fuel pressure. The QSK-19 fuel system, however, controls fuel pressure by electronically adjusting flow areas of the actuators. For an example of the pressure time concept, let's consider the following. With equal sources of pressure connected to passages of different flow areas, if both systems are allowed to flow for the same amount of time, more fluid will be collected in the container of the system with the larger flow area. Therefore, with fluid pressure and flow time held constant, the flow area determines the quantity of fluid collected. If passages of equal flow area are now connected to unequal sources of pressure, and the time the fluid is allowed to flow is held constant, more fluid will be collected in the container of the system that has a greater source of pressure. Thus, if the flow area and flow time are held constant, the pressure determines the amount of fluid collected. Finally, if passages of equal flow area are connected to equal sources of pressure, the time the fluid is allowed to flow will determine the amount of fluid collected. Thus, if the flow area and fluid pressure are held constant, the time determines the amount of fluid collected. These three illustrations provide an excellent example of the pressure time concept used in the QSK-19 fuel system, rail, and timing systems. The control valve assembly receives fuel flow from the fuel pump. Inside the control valve assembly, the fuel flow divides to supply both control systems. The control system that maintains fuel rail pressure consists of a rapid restart fuel shutoff valve, fuel rail actuator, and fuel rail pressure sensor. Fuel flows through the rapid restart fuel shutoff valve first, and then to the fuel rail actuator. The actuator is an electronically controlled spool-type control valve. The coil receives a PWM signal from the ECM. Depending on the signal from the ECM, the spool will move to the left, uncovering the inlet port and allowing fuel flow. The fuel rail pressure sensor monitors this pressure and sends this information to the ECM. The fuel rail actuator valve has a maximum flow rate of 1,000 pounds per hour. The control system that maintains the timing rail pressure consists of a timing rail actuator and timing rail pressure sensor. Fuel pressure in the timing rail is controlled by the timing rail actuator, which is also controlled by the ECM. The timing rail pressure sensor monitors the pressure and sends this information back to the ECM. The timing rail actuator has a maximum flow rate of 1,500 pounds per hour. Fuel flows from the control valve body through the fuel transfer tubes to the fuel manifold. There are two manifolds, the front manifold serving cylinders 1 through 3, and the rear manifold 4 through 6. Each manifold has 3 passages: timing rail, fuel rail, and drain. Drillings in the cylinder head intersect with the fuel manifold. Timing fuel and rail fuel pass through the cylinder head to the injector. Drain fuel from the injectors passes through the cylinder head to the fuel manifold. We will talk about the QSK-19 fuel system injectors later in the program. In applications where the fuel supply tank is higher than the engine, a check valve prevents drain fuel from flowing back into the system when the engine is not in operation. The correct fuel temperature is critical to the proper operation of the QSK-19 fuel system. Thus, a fuel cooling radiator is mandatory. Drain fuel from the fuel manifold is directed to a thermostat at the cooler. At 89 degrees Fahrenheit, the thermostat is closed and no fuel flows through the cooler. At 90 degrees Fahrenheit, The thermostat starts to open and is fully opened at 104 degrees Fahrenheit. This causes all drain fuel to flow through the cooler. Although heat is dissipated from the fuel by the supply tank, the use of the fuel cooler ensures positive temperature control. The typical drain fuel flow rate is 2 gallons per minute. Also, the cooling radiator can have no more than a 5 psi restriction. The QSK-19 fuel system injector shares many design features with PT and Select. It represents, however, the next generation in technology. The new QSK-19 fuel system injector will be capable of up to 35,000 psi of fuel injection pressure in the future. Currently, pressures are in the 25,000 psi range. The new injector has 3 individual moving sections: the lower plunger, the timing plunger, and the upper plunger. All of these plungers are coated with titanium nitride to resist scuffing wear and provide maximum service life. The lower part of the injector is very similar to the PT injector. The plunger and nozzle are shaped like the PT. The fuel supply, metering, drain, and check valves are also similar to the PT system. One important difference is that the lower barrel and nozzle are one piece. This design eliminates high-pressure joints. The open nozzle design of the injector provides the ideal rate and shape of injection. A slow start of injection allows a slower burn at the beginning of combustion for reduced combustion noise. The sharp end of injection, eliminating secondary injection, provides reduced hydrocarbon emission. For every injection cycle, the stroke of the lower plunger is 10 millimeters. The QSK-19 fuel system provides infinitely variable injection timing. The timing is varied by controlling fuel pressure to the injector timing section. The timing section consists of a balance orifice, timing plunger, and deflector ring. The timing plunger is positioned to the barrel bore below the upper plunger. The upper section of the injector consists of the barrel, spring housing, return spring, upper plunger, top stop cap, and plunger link. Theory of operation. We will start the injection cycle with the cam follower on the outer base circle. All 3 plungers are in contact with each other. As the camshaft rotates, the follower rolls toward the inner base circle, which causes all 3 plungers to retract. When the lower plunger retracts far enough, the rail feed port is uncovered, and fuel is PT, pressure time metered, through an orifice into the cup. Remember from PT theory, the P is rail pressure, and T is the time that the feed port is uncovered. The time will depend on engine speed. The rail pressure will be controlled electronically and can be as high as 290 psi or as low as 2 psi. The lower plunger is in its fully retracted position when the spring retainer contacts the ledge. The cam follower continues to roll toward the inner base circle, allowing the timing and upper plungers to continue moving upward. When the upper plunger retracts far enough, it uncovers the timing feed port, and fuel is also PT metered through an orifice into the timing chamber. As the cam follower starts up the injection ramp of the camshaft, the upper plunger will move down and close the timing feed port to end timing metering. The fuel that is metered into the timing chamber is now trapped between the upper plunger and the timing plunger. The amount or volume of fuel metered into the timing chamber determines the separation between the upper and timing plungers. The amount of separation determines the effective length of the injector plunger. This length determines when injection will start. Changing the overall plunger length changes the start of injection. The separation between the plungers varies from a minimum of 2 millimeters to around 9 millimeters. This separation is sometimes referred to as overtravel. The trapped fuel becomes a solid link and all three plungers move down together. As the lower plunger moves, the rail feed port is also closed. The timing and upper plungers have a diameter of 15 millimeters compared to the 11 millimeter diameter of the lower plunger. This difference in diameter reduces the pressures in the timing chamber to approximately 50% of the injection pressures. Therefore, if the pressure in the timing chamber is 12,500 psi, pressure in the cup can be as high as 25,000 psi. This reduction ratio allows the injector train to operate with minimum stress and wear, yet still produce extremely high injection pressures. The downward velocity of the plungers will increase as the follower continues up the injection ramp of the camshaft. When the pressure in the cup exceeds the pressure in the cylinder, injection begins. Injection ends as the lower plunger makes contact with the nozzle seat. At approximately the same time, the groove in the timing plunger aligns with the groove in the barrel, opening the spill port. The timing fuel then spills as the upper plunger continues its stroke. During this spill process, the drilling in the timing plunger regulates the fuel pressure in the timing chamber to keep a load on the lower plunger. This pressure is necessary to prevent the lower plunger from lifting before mechanical contact occurs between the upper and timing plungers. A spill ring is positioned over the spill port because the timing fuel spilling from the chamber is under pressure. The spill ring acts as a pressure deflector to prevent damage to the injector bore in the cylinder head from the continual release of high-pressure fuel. During the last 5 millimeters of upper plunger travel, the nose on the bottom of the upper plunger engages with the port in the timing plunger. The clearance between the two ports acts as an additional flow restriction on the fuel in the port. This additional restriction keeps pressure on the lower plunger while the rest of the timing fuel is spilling. This feature is needed to ensure that the lower plunger does not unseat during the transition from the ramp to the nose of the camshaft lobe. As all of the timing fuel spills from the chamber, the plungers will make mechanical contact. The downward travel of the injector train will continue, creating a mechanical crush condition on the lower plunger. This ensures that the plunger remains sealed in the nozzle during combustion. By now, we should have a good grasp of the fueling and timing concepts involved with the QSK-19 fuel system. So, let's take a close look at how electronics control the engine fueling. The QSK-19, like the other Cummins electronic engines, is commanded by an electronic control module, or ECM. The QSK-19 fuel system, ECM, contains the latest technology from Cummins Electronics. It has 2 microprocessors to process and manage the data necessary to operate the engine and systems. It also contains 2 megabytes of memory to store calibration and fault data. The ECM's main task is to manage the fuel control system that operates the engine. The ECM samples all inputs, processes the data, and outputs signals to the rail and timing control actuators many times each second. The ECM can make changes to rail and timing pressures very quickly, responding instantly to the slightest variations in operating and environmental conditions. For example, look at when the operator opens the throttle to increase engine speed. The ECM will consider the request for increased engine speed, the actual engine speed, and all other inputs. It will then compare this data to its calibrated data to determine the appropriate signal changes. If additional engine speed is allowed, the ECM then outputs the appropriate signals to the fuel rail control actuator to increase engine RPM. If this increase in engine speed requires a change in injection timing, the ECM will output the appropriate signals to the timing control actuator as well. From the previous overview, we should have a good idea of the basic system operation. Now, let's look at each subsystem and the components that make up these systems. We'll start with the inputs. The ECM utilizes input information to determine engine, fuel, and timing pressures, or more simply, to operate the engine. The inputs are divided into the following: sensor inputs, switch inputs, operator inputs, feedback inputs, and possible feature inputs. There are two temperature sensors. The temperature sensors provide critical temperature information to the ECM. The temperature sensors are coolant temperature sensor and intake manifold temperature sensor. The coolant temperature sensor is mounted in the thermostat housing. The information this sensor obtains is utilized by the ECM to help make decisions for timing and engine protection. The intake manifold air temperature sensor is mounted in the aftercooler housing and measures air temperature after the cooler core. The information this sensor obtains is utilized by the ECM to help make decisions for timing and engine protection. There are 6 pressure sensors that provide critical information to the ECM. The pressure sensors are fuel rail pressure sensor, fuel timing pressure sensor, oil pressure sensor, coolant pressure sensor, boost pressure sensor, and ambient air pressure sensor. The fuel rail pressure sensor is mounted in the fuel control valve assembly and measures actual fuel pressure in the rail supplying the injectors. The fuel timing pressure sensor is also mounted in the fuel control valve assembly. It measures actual fuel pressure in the rail supplying the timing chambers. The oil pressure sensor is mounted in a main rifle port above the ECM. It measures main system oil pressure. The information this sensor obtains is utilized by the ECM to make decisions for engine protection. The coolant pressure sensor is located in the oil cooler housing. It measures coolant system pressure. The information this sensor obtains is utilized by the ECM to make decisions for engine protection. The boost pressure sensor is mounted in the aftercooler housing and measures air inlet pressure after the turbocharger. The information this sensor obtains is utilized by the ECM to determine accurate engine fueling. The ambient air pressure sensor is mounted on the fuel control valve assembly below the ECM. The ECM utilizes the information received from the sensor to make decisions for engine protection. In high-altitude operation, the engine is derated to prevent turbocharger overspeed. The engine speed sensor is located in the back of the front gear housing. It detects 24 raised pads on the back of the camshaft gear and sends signals to the ECM. The ECM processes these signals to determine engine speed. The sensor has a dual signal output providing two separate signals to the ECM. Even if one signal is lost, the engine will continue to operate. There can be two system switches. They are idle validation switch and coolant level switch. The idle validation switch is located in the throttle pedal assembly. It provides a confirming signal to the ECM as to the position, released or depressed, of the throttle pedal. The coolant switch monitors the coolant level in the radiator top tank. If the fluid level drops below a predetermined point, the switch will open, indicating a low fluid level to the ECM. The information this sensor obtains is utilized by the ECM to make decisions for engine protection. In addition to monitoring the fuel and timing pressure sensors to determine actual pressures, the ECM also monitors the current returning from the rail and timing control actuator valves. This feedback information provides confirmation of correct valve operation. The two main inputs from the operator are the key switch and the throttle. The position of the key switch determines the state of engine operation, on or off, and the position of the throttle determines the desired engine speed. The other possible feature inputs modify engine operation and are provided by switches. The intermediate speed control feature will be discussed later. Some of these inputs are alternate droop, intermediate speed control, alternate torque, and alternate low idle speed. There are 6 system outputs. 3 of the outputs control the fuel rail, timing rail, and fuel shutdown functions. The fuel and timing control actuator valves are spool-type valves. The spools are controlled by an electromagnetic device which is commanded by the ECM. The ECM produces the following signals: fuel control actuator valve signal, PWM, pulse width modulation, duty cycle. Timing control actuator valve signal, PWM duty cycle. Fuel shutoff, power to the shutoff solenoid valve. The remaining 3 outputs are for system information: diagnostic lamps, fault communications, data link, system programming, tachometer, output signal for tachometer operation. The QSK-19 fuel system is capable of providing 2 types of engine governing: automotive type and variable speed VS type. Both of the governor types are programmable through calibration. The automotive governor maintains engine speed based on throttle position and engine load. The percent throttle determines the available engine torque. With the throttle in a fixed position, engine speed will drop as the load is increased. The automotive governor would be selected from the Features screen in the Features and Adjustable Parameters function of Insight. In the Performance Data screen, the parameters shown can be set for the automotive governor. Breakpoint 1 speed is the RPM at which the fuel curve transitions to high idle droop. Droop at breakpoint 1 is the percentage droop setting at this RPM. Droop at maximum throttle is the percentage droop setting at maximum high idle RPM. Droop at minimum throttle is the percentage droop setting at idle RPM. Engine speed provides idle speed setting. The variable speed governor varies engine speed in direct relationship to throttle position. The governor tries to hold the engine speed constant at a fixed throttle position. The variable speed governor would also be selected from the Features screen in the Features and Adjustable Parameters function of Insight. In the Performance Data folder, the same parameters as were set for the Automotive Governor can also be set for the Variable Speed Governor. The QSK19 fuel system offers up two intermediate speed control settings. In an intermediate speed control mode, the engine speed is controlled to a pre-programmed value regardless of throttle position. A separate droop percentage can be set which applies to all switched intermediate speeds and will be in force while the engine is in intermediate speed control. The low idle speed setting is set by calibration. It can, however, be modified by the increment-decrement switch. The speed can be increased or decreased by toggling the increment-decrement switch. The QSK19 fuel system features an engine protection system that is designed to prevent engine damage due to prolonged exposure to extreme conditions. The ECM monitors the following systems to provide this protection: coolant level, coolant temperature, oil pressure, and intake manifold temperature. Engine protection can also be enabled or disabled from the feature screen in Insight's Features and Adjustable Parameters function. Engine protection shutdown is also enabled or disabled from this screen. When the ECM detects an out-of-bounds condition, a series of protective actions is initiated. The action initiated is dependent on the severity and duration of the condition. The protective actions are as follows. Engine protection lamp is lit and a fault is logged. Engine torque and/or speed is derated. Engine shutdown is activated. The first level of protection is the engine protection lamp. When a parameter being monitored goes out of bounds, the ECM lights the engine protection lamp and logs a fault. The engine protection lamp is the operator's first indication that a system parameter is out of bounds. After turning on the engine protection lamp, the ECM starts recording elapsed time and monitors the severity of the event. If either duration or severity exceed a pre-programmed value, the ECM initiates a torque and/or speed derate. After a derate is initiated, the ECM will continue to monitor both duration and severity and will shut down the engine if the condition is not corrected. The engine shutdown feature can be overridden through OEM calibration options. The QSK19 fuel system will automatically derate the engine at a predetermined altitude. The ECM determines altitude by monitoring ambient air pressure and, using calibration tables, determines the altitude derate. If the engine speed exceeds a predetermined RPM, the ECM will remove power from the fuel shutdown solenoid valve, stopping fuel flow to the system. It will also log a fault and continue recording engine data. When the engine speed drops to a predetermined RPM, the ECM will apply power to the shutdown solenoid to restart the engine. The ECM can be programmed to deny engine restart if a predetermined number of shutdowns has occurred. This prevents the use of the engine when an intermittent problem exists. Diagnostics. The engine protection lamp is used to warn the operator of the following conditions: coolant, intake temperature out of range; oil, ambient pressure out of range; coolant level out of range; fuel temperature out of range. The protection lamp will light and stay on as long as any of these conditions exist. The yellow warning lamp is used to warn the operator that a component or system has logged a fault. The vehicle can continue operation, but the conditions must be corrected as soon as possible. The red engine stop lamp is used to warn the operator that a major system problem has occurred. The vehicle should be shut down as soon as possible. The diagnostic switch is used in conjunction with the yellow and red fault lamps to display active fault codes. With the engine not running and the key switch in the on position, move the diagnostic switch to the on position to check for active fault codes. The fault code flash process sequence begins with the yellow warning lamp flashing once. There will be a short 1 to 2 second pause, and then the red stop lamp will flash out the 3-digit fault code. There will be a short pause between each digit in the code. After the code has been flashed, the yellow lamp will flash, and then the red lamp will again flash out the same fault code. The system will continue flashing this same fault code until the diagnostic switch, increment-decrement switch, or key switch is activated. To display the next active fault code, move the increment-decrement switch to the increment position. If there is another active fault code, it will flash out as before. If there is only one active fault code, that code will flash out again. If there are multiple active fault codes, use the increment-decrement switch to move through the list. The increment position will move forward through the fault list, and the decrement position will move backward through the list. If you move completely through the list of codes, you will come back to the first code again.